Eigenfaces, face recognition with principal component analysis. The goal is simple: turn thousands of raw pixels into a compact representation that still preserves identity. Imagine a database of faces. A new face comes in. You need to find its match. A computer doesn't see a nose, a smile, or a jawline. It sees numbers. Thousands of numbers. So, how do you compare thousands of numbers efficiently? To answer that, we will make 5 things explicit: the problem, the core idea, the processing pipeline, the advantages, and the limitations. Before we get to eigenfaces, let's name the problem. A face image feels simple to us. But to a computer, it begins as raw pixels, thousands of brightness values, lined up with no meaning attached. Here is a face. Or rather, here is what a computer sees when it looks at a face. A grid. Each cell holds a single number, its grayscale brightness. 0 is black. 255 is white. Everything between is a shade of gray. Now watch. We flatten this grid row by row into a single vertical list. This list is a vector. For our small 4x4 example, that's 16 numbers. For a real 64x64 face image, that's 4096 numbers. Every face is now a point in a 4096-dimensional space. Recognition becomes a geometry problem. Given a new facepoint, which stored facepoint is closest? Here are 2 photos of the same person. Different lighting. To you, obviously the same. But look at their pixel vectors side by side. The distance is enormous. Not because the faces differ, but because the light moved. Comparing all 4096 raw dimensions is slow, and it's dominated by noise, lighting, shadows, camera angle. None of that tells us who the person is. The key insight: face images don't scatter randomly through 4096 dimensions. They cluster near a much lower dimensional surface. If we can find that surface, we can work there instead. Before we find that lower dimensional surface, we need to prepare our data. We have m training face images. Each is a vector. Together they form a matrix X, 1 face per column. Step 1. Compute the average face. Average every pixel position across all m images. The blurry result you see is the mean face. Step 2. Subtract the mean from every face in the dataset. Watch each image transform. Brighter patches appear where this face is above average. Darker patches where it is below. What remains is not the face, it is the deviation. The fingerprint of what makes this person different from the average. Now look at the point cloud. The entire cluster shifts. We've moved every face point so the center of the cloud sits exactly at 0. All coordinates. The origin. Why does this matter? Because now when we measure how the cloud spreads, we measure pure variation, not contaminated by where the center happened to land. Every step from here uses these centered faces. The cloud is centered. Now we ask, in which directions does it spread the most? Watch this axis rotate through the cloud. At most angles, the spread is uneven. But at one angle, it maximizes. The data stretches as far as possible along that direction. That is the first principal component. The direction of maximum variance. The covariance matrix C encodes all of this. It captures how every pair of pixel positions varies together across the whole dataset. But C is 4096 by 4096. Over 16 million entries. Expensive red block, computing its eigenvectors directly is slow. Turk and Pentland found a shortcut. Cheap green block, instead of the large n by n matrix, compute the small m by m matrix, one entry per training image, not per pixel. The eigenvectors of the large matrix are recovered exactly by multiplying the small eigenvectors back through the data. We solve the eigenvalue equation. Each eigenvector v is a direction in face space. Its eigenvalue lambda tells us how much variation lies along that direction. Larger lambda, more variation captured. Now, each eigenvector has 4096 components, the same length as a face. So we can reshape it back into a 64 by 64 image. These are eigenfaces. Ghostly, blurry face-like patterns, each one a fundamental mode of variation across human faces. Lighting direction. Width. Eye spacing. Expression. The first eigenface captures the most variation. Each subsequent one captures less, independently of all the others. In practice, the top 50 eigenfaces capture over 95% of all the variation in the dataset. Here is how recognition works. Take a new centered face, phi. We pass it through each eigenface, one at a time. Each pass gives us one number, a weight, omega k. How much of this eigenface is present in this face? Collect all k weights into a vector, capital Omega. Instead of 4096 numbers, we now have k 50, typically. That is this face's address in face space. To recognize a new face, compute its weight vector, then find the stored face whose weight vector is closest. Euclidean distance in k dimensions. Fast. Reliable. Elegant. We can also run this backwards. Reconstruct a face from its weight vector. Add the mean face back. Then add each eigenface, scaled by its weight. The result is an approximation of the original. With just 5 components, a ghost of a face. The rough shape is there. At 20, recognizable. The major features emerge. At 50, a clear likeness. At 100, fine detail. Creases. Shadows. The specific contours of this person's face. What if the input is not a face at all? A car, forced through the eigenface pipeline. The reconstruction is a haunted blur. Face space has no vocabulary for a car. The reconstruction error gives us a detector. Not just, who is this face, but, is this a face at all? All of this maps directly to a few lines of standard number py. Load the faces, flatten them, stack them into a matrix. Compute the mean. Subtract it. The cloud shifts. Form the small m by m surrogate matrix. Solve for its eigenvectors. Multiply back through the data to recover the full eigenfaces. Watch the variance curve climb. By 50 components, over 95% of the information is preserved. Before we close, here is the whole method in one pass. The problem: raw face images are huge vectors, and raw pixel distance is noisy. The core idea: faces do not fill the whole pixel space. They lie near a much smaller face subspace. The process is: center the data, measure covariance, find eigenfaces, project each face into weights, then compare those compact weight vectors. The advantages are clear: fewer dimensions, faster matching, interpretable components, and reconstruction error that can help reject non-faces. But there is one honest limitation. Watch this face rotate in 3 dimensions. As the pose drifts away from frontal, the linear PCA projection warps. It cannot follow a curve it was never designed to represent. Text card 1, sensitive to lighting and pose. Text card 2, linear method, misses non-linear structure. Text card 3, superseded by deep CNNs and accuracy. These are real weaknesses. And yet, Eigenfaces didn't just solve a problem. They gave us the vocabulary, feature spaces, dimensionality reduction, compact representations. A language every modern face recognition system still speaks. This video is based on the original work of Turk and Pentland, published in the Journal of Cognitive Neuroscience in 1991, and Chapter 3 of the Handbook of Face Recognition, 2nd edition, edited by Jain.